Good morning, students. I am Dr.R.Suganya, Department of Computer Science with Cybersecurity. Today I am going to say about asymptotic analysis. Okay, so about this, it is very efficient for understanding that how the software scales by exploring fundamental mathematical bounds of computation will be. Okay, so it is like algorithm performance. Okay, so actually asymptotic analysis is like how you computate, okay, with the thing is like the vital role of modern software engineering and design. Okay, we can exactly say it like that. It is a part of a large analysis. Okay, so on engineering and design, so that we call it as asymptotic analysis. So here the core mathematical technique and what will be the machine independence and what will be the performance scalability on when we do this algorithmic calculations. So the core mathematic technique will be used to understand how algorithm behave as their input size which grows, focusing on runtime as well as a space, memory space. Okay. In machine independence, like abstracts away specific hardware constants and implementation details for standardized comparison. And the performance scalability with large inputs to aid in better software decisions. Okay. And next is about why complexity analysis matters. So here algorithm comparison and the resource management and also the scalability insight. Okay, so here the algorithm is like how it can be that is be designed on time. Okay, that is matter for independent complexity. And the resource management, like how it deals with the data sets to ensure the performance solutions. And scalability insights, which means that how much time and space will it consume as the input scales. That is the thing. So resource management, that is like to deal with large data sets. So this is what a three complexity thing. And the asymptotic toolkit. Okay, so the three primary mathematical notation used to bound this algorithm are like theta, okay, that is big O, and omega. Okay, so big O is represents the upper bound, describing the absolute worst cases scenario for execution time only. And omega 3 is like lower bound, indicating the best case performance or minimum time needed. And theta b, which represents the tight bound, providing a precise estimate when best and worst case coverage. Okay. Next comes the worst case, that is big O notation, which means like how it can be represented, like a concept in it is a performance or complexity. Okay, so which has several sections including upper bound and dominant terms like examples. Okay, and the code examples like the simple for loop 1 to n and finding maximum in an array. And dominant term section probably discusses to identify the most significant terms in an algorithm complexity, ignoring the lower order terms. Okay, and the best case, the omega notation. Okay, here which have the infographic things consist of three rectangular boxes, like lower bound math, the middle box is pink, that is worst quick sort, and the bottom box minimum insights. Okay, so that is what is to better understand the context. It will be like and we have like appears by discussing the omega, like the contest algorithm. Okay, and next is exact behavior, binary search tree, and average case analysis. So here the thing is bounds algorithm rate from both above and below the same mathematical notation, binary search cases, and average case analysis. Okay, so it is the tight bound theta notation. And next is efficiency in action, and that is linear search, binary search, merge search, and bubble sort. Okay, and here we have main thing, how the notation is being used and what will be the performance class is used and what is the scalability. So the highly scalable that thing that we use here is binary search. Strategic analysis roadmap, prioritize that big O. Okay. And we have like a diagram, identify the tight bounds and continuous practitioners. Okay. So the data visualization, the diagram itself could form of representing the relationship between the entity and the concepts. Okay. So big O, that is notations used. Okay. Active, that is high ranking. Okay. So in the hexagons are arranged in a hierarchical structure where the largest hexagon is the center and the smaller ones branching out from it. Okay, that is what is the thing. Next is about building better algorithms. So optimize efficiency and exploring big O, omega and theta to become more effective software engineers. Okay, and thank you.